Hi everyone. We appreciate the opportunity to present our paper, Pharmacokinetics-Informed Neural Network for Predicting Opioid Administration Moments with Wearable Sensors. This work is a collaborative effort between Hologilo Data Science Institute at University of California, San Diego, UMass Medical School Division of Medical Toxicology, and University of Utah's College of Social Work. My name is Bhanu Teja Gullapalli. I am a final year PhD student at University of California, San Diego, and today I'll be presenting this work. So let's get started. What are opioids actually? Opioids are a class of drugs that are prescribed by healthcare professionals to treat pain. However, repeated usage of this drug can cause an individual to become dependent on opioids. This includes having a condition of addiction that leads to opioid misuse disorder and potentially be life-threatening. A natural solution to this problem would be, why not have an information chart of opioid information usage, and healthcare professionals can use this information chart to determine and prescribe future opioids accordingly. Well, the current solutions are not far from this. Individuals self-report their usage patterns to healthcare professionals. However, self-reports suffer from inaccuracies due to recall bias and intentional concealment of use. Biological sample testing such as urine, blood, or hair testing exists. However, these suffer from limited windows of detection and inability to provide precise information about timing and dosage patterns. To overcome these challenges, we would like to build digital biomarkers for opioid administrations. What are these? What are digital biomarkers? Well, these are technologies existing in current wearables that give information about a certain health-related metrics, like Apple Watch providing information about irregular heartbeat from ECG. Similarly, a Dexcom device providing information about type 2 diabetes spikes from your glucose levels. We want to build a similar solution that uses wearable data from a wristwatch to provide opioid administration information. In fact, what we did in our previous work was not far from this. We built OpiTrack, a wearable-based solution to detect administration given through intravenous route, that is directly to the blood. We built a temporal attention-based model, CTA-TCN, motivated by the statistical findings to detect intravenous administrations. While this work was important, most prescription opioid administrations happen orally after an individual gets discharged from the hospital. And that's the problem we would like to solve in this paper. We want to detect oral prescription opioid administrations using wearable data. Essentially, given a time series data from a time window, we predict two things. First, whether an administration occurred in this time window or not, a simple yes or no answer. The second, when exactly an administration happened in this window, if the answer to the previous question is yes. To validate this hypothesis, we collected a data set that included both inpatient and outpatient setting. We collected a total of 2,910 hours of wearable data containing 227 oral opioid administration from 42 participants. Again, this data included both in-hospital inpatient setting and outpatient real-world setting. As we already built a model for IV administrations in our previous paper, OpiTrack, why not reuse the same model for detecting oral administrations? What's the worst that could happen? Well, we did this, and we observed that this model performs very poorly for both in-hospital and outpatient setting. Why are the results very poor? Why is this happening? The answer lies in drug plasma concentration. The drug plasma concentration is the amount of drug present in the bloodstream after an opioid administration occurs. And this concentration varies differently based on the route and the type of opioid. For intravenous, as the drug is administered directly to the bloodstream, the peak effect of the drug reaches much faster as compared to oral opioids that needs time for digestion and that reach the peak effect much later on. Again, based on short-lasting or long-lasting type of drug, there are differences within oral administration also. The physiological changes occurring in the body are directly related to this drug plasma concentration. Therefore, a same model won't work for all. We would like to build a new model for oral administrations. While building this model, the first difference we observed in these different types of administration is the rate of change in the drug plasma concentration being different. What I mean by this is the peak effect being varied based on the type of route. For IV, it takes up approximately, for the intravenous route, it takes approximately 60 to 90 minutes to reach the peak effect. the peak analgesic effect, whereas for oral administration, it takes approximately 2 to 6 hours. The consequence of this is that we would require much larger time windows when predicting opioid administrations in oral route as compared to intravenous route. In our dataset, we included a total of 4 hours of oral opioid data, whereas in IV administration, this is approximately 90 minutes. As a consequence of this large time window, the effective sample points decreases, and not just that, it's very expensive to collect labeled wearable data in substance use disorder. To overcome these solutions, we pre-train the models to effectively use the data and have good initialization points before we go on to our final downstream or fine-tuning task of predicting our administrations. But how do we determine the artificial task in this pre-training or in the self-supervised setting? Well, we go back to our previous paper again. In our previous paper, we showed that whenever an opioid administration occurs, there are physiological changes occurring in the body. Essentially, we observe that there are statistical differences in the signals before, pre, and post-opioid administration. Motivated by this, we design the artificial task, the self-supervised task accordingly. We take the time window, we modify or not modify the signals in this window with a certain probability. If it is to be modified, we modify random modalities of the signal starting from a randomly selected time point. Modification here represents either amplifying the signal or reducing the signal by a certain factor. And the task essentially becomes, given a time series window, whether we actually modified the signals in this time window like a yes or no, and if we modified the signals, when exactly the modification occurred. If you compare this to our downstream task or our final task, we see a lot of similarities. The artificial data, whether it's been modified yes or no, is very similar to whether there is an opioid administration occurring in the window, yes or no. And if the data has been modified, here we are detecting the time of modification, whereas in the downstream task, we are detecting when exactly the opioid administration occurred. So overall, the overall architecture using self-supervised learning looks as follows. We pre-train the model initially, and we fine-tune it to our downstream task. We test this architecture using different models, not just with CTA-TCN, but with other time series models. And what we observed was that, consistently across all the models, we observed that self-supervised learning improved performance. Unfortunately, for opioid moment prediction, we observed that the performance is still not high enough for generalizability. We observed 0.53 R-square to be the max value in inpatient setting and 0.43 R-square to be the maximum in outpatient setting. How do we improve this opioid moment prediction? We go back again to the drug plasma concentration, and we revisit a new topic. We use the knowledge from opioid pharmacokinetics. So essentially, pharmacokinetics is a branch of pharmacology that deals with how body affects the drug. It provides information of how a drug is being absorbed and how it is eliminated over the time. The pharmacokinetics gives equations to describe this blood plasma concentration over the time. The drug used in our study, oxycodone, is defined by this first order equation. The drug used in our study, oxycodone, is the drug plasma concentration over time for this drug is defined by the first order equation as follows. It's directly proportional to the dose times e power minus ket and e power minus kat, where ke and k are the absorption constants and t being the time of administration. From the EHR and wearable data, we have all the information we need for this equation. We have the time of administration. We also know what type of opioid the user is administering. We use this information to approximate this blood plasma concentration over time. And we use this blood plasma concentration as an auxiliary task during the training. So if we go back to our previous architecture, where we fine-tuned the self-supervised model to predict the administration detection and moment prediction. Now, during the training process, we add a new task where the model has to predict the blood plasma concentration, the plasma drug concentration over the time, along with the detection, and moment prediction. We observed that injecting this pharmacokinetics information to the existing architecture uh, improved the performance, and not just with, again, similar to the self-supervised learning, the improvements is not restricted to one model. We observe this improvement consistently across all the models. Uh, yeah. Essentially, we showed that we can detect oral opioid administrations using self-supervised learning and drug plasma concentration by using it as an auxiliary task. What lies next? In the current study, we use prescription opioids of type oxycodone that followed first-order elimination and absorption. We want to extend this idea to other types of opioids where, where, the, where the plasma concentration over time is given by varying orders of equation. For example, fentanyl, which uses third-order equation for absorption and elimination. Similarly, we also observed that individuals that are dependent on drug tend to simultaneously combine multiple drugs. Given this scenario, where an individual administers multiple types of drugs simultaneously, and as all the drugs tend to have effect on physiological signals, it is important to identify the effect of an individual drug, like a drug of opioid individually. And that's what we would like to do next. Uh, and that concludes our work. Thank you very much. Um, if you would like to call me, mail me, you can find my information here. If you would like to visit me, I'll be in UC San Diego for next couple of months. We can have a chat. Thank you very much.